In this lesson, we're talking about graphs of our quadratics, looking at some important pieces here, attributes, and interpreting them in real life situations. So just going back to our basic here with our points A, B, C, and D. A and D, notice how they are crossing the x-axis. The points A and D are going to be our x-intercepts. However, throughout our unit concept here, they are also known as zeros, and they will also be referred to as roots. And so just to practice identifying, point A is at -3, 0, and point B, the other x-intercept, right, because it's crossing the x-axis, is at 1, 0. Then looking at point B, notice how this is the very top, right? So with our parabola, so this is our quadratic, the U shape. With our parabola, notice how point B is the highest point that this graph reaches. So this is our vertex. And the vertex can either be, like this example, a maximum, or it could loop down and have a minimum, be a minimum point. And so in this case, our maximum, our vertex, point B, is at -1, 4. So -1, 4. Then point C. Well, now notice C is crossing the y-axis. So C is our y-intercept. And point C is at 0, 3. So these are the points that we'll be focusing on, but when we are interpreting real life situations with our quadratics, our parabolas. So like looking at example 1. Here, this graph just represents a ball being thrown in the air. So time is always going to be kind of like that independent variable. So you're going to see time a lot on the x-axis, and you're going to see height or distance or anything of that sort here, right, as your y. So here, what is the y-intercept? Well, where is our graph crossing the y? Right here at 0, 0. That's the starting point. Now, one of the x-intercepts is 5, 0, right here. So what does it mean in context of this situation? Well, if you think about it, the ball started here, right, on the ground. Let's say this is a soccer ball, right? Because a soccer ball, you kick it and it starts on the ground. You kick it up in the air, and then the ball comes back down, right? And boom, it hits the ground. So what does this x-intercept represent? Well, it represents how long the ball was in the air. So this ball in this case was 5 seconds in the air. So that represents how long the time that the ball was in the air. So it lasted 5 seconds before it hit the ground. What is the vertex? So here, looking at the vertex, well, again, right, the vertex is the maximum minimum point. So here's our maximum, which would be, let's say, about 2.5, 40. And what does it mean in this situation? Well, what does the 2.5 represent? 2.5 represents seconds, right? That's your time. What does the 40 represent? Well, the 40 represents your height in feet. So what this means is that it took the ball 2.5 seconds to reach the maximum height here of 40 feet. So looking here at example 2, so let's do another. Here again, we're talking about the height of a batted ball. What is the y-intercept? So here now notice if it's like a batted ball, does it start on the ground? No. Notice now how here's our y-intercept where it's crossing the y. So let's say that this is about 0, 6. So what does it mean in context of the situation? So like what I was just talking about. If this is a batted ball, right? Like a baseball player is up at bat and they hit the ball. Well, does it start at the ground? No. This is saying that the ball is starting at 6 feet. So the start of the ball is at 6 feet. That's where it started. That's its starting height. What is the vertex? So here we go. So remember vertex, right, is the highest point. So here, that's 0.5. So maybe about, yeah, this is a little rough here. We can say like maybe 0.75 or 0.8. Let's say 0.8. 0.8, 15. And what does it mean in context of the situation? Well, again, what does the 0.8 represent? Time in seconds, right? So this is our seconds. And then the 15 represents what? Feet, the height. So what does this mean in context of this situation with the batted ball? It took 0.8 seconds for that ball to reach its maximum height of what? 15 feet. So then here, what is our x-intercept? So the x-intercept right here, right, where it's crossing the x-axis, which is at 2, 0. And what does it mean? Well, it means we started here and then it reached its max, but then it's got to come down eventually, right, to right here. So the ball was in the air 2 seconds. Or it took 2 seconds for the ball to reach the ground, however you want to put it. So go ahead and pause the video and try this you try here on your own. And now let's see how you did. So for the first question, how long was the football in the air and what coordinates represent the length of time? Well, the football started here on the ground and then it took about 6 seconds. So the ball was in the air for 6 seconds. And what are the coordinates? The x-intercept, which is here at 6, 0. Then how high did the football reach in the air? Well, that's basically asking what is the maximum height that the football reached? The maximum was 30 feet. And again, what coordinates tell us this? The vertex, the maximum, which was here at 330. So that will tell you that maximum, how long and how high it got. So here's now, again, another problem with Melissa launching a rocket from a platform. And some of these questions you can do, like these first couple of questions, so I'll quickly go over those, but adding a little bit more to it. So just being able to interpret the graph now, looking at other points on the graph. So like here, for example, what is the initial height of the launch? Where did the launch start? Right here, the y-intercept. So let's say that's about approximately, let's say 3. So approximately 3 meters, because now our height is in meters. So about 3 meters, that's where the rocket started. What is the vertex? So the vertex, our maximum, which is here at 2.5, 34.25. And what does it mean? Well, again, what does this mean? 2.5. 2.5 what? Seconds, right? 2.5 seconds, 34.25 what? Meters. So again, what does this mean? That it took the rocket 2.5 seconds to reach its maximum height of 34.25 feet. Now let's look at the next. After 1 second, how high above the ground is the rocket? So after 1 second, so here's 1. After 1 second, how high above the ground was the rocket? So here's our point, which is 23 meters. So what if the point is not necessarily given to you? Still the same thing, right? So see if you can identify after 4 seconds, how high above the ground is the rocket? And so here at 4 seconds, right here, at 4 seconds, I would say, let's say about 22 meters. How many seconds does it take for the rocket to reach approximately 30 meters? So now we're looking at 30 meters, which is here. And here it takes about 1.5 seconds. Now, this is a new introduction to a vocabulary. What is a reasonable domain? Whenever we talk about domain, and we'll talk about this more, but domain is the x values, all of the x values that the graph covers. So like looking at this graph here, what x value does it start at? Well, it starts at 0. And where does it stop? Well, just past 5, right? Right here. So we could say that's about 5.1. So the domain, or reasonable domain, and we'll talk about this more when we get to other graphs in our next. What is the reasonable domain for this graph? Well, that is from 0 to 5.1, because the graph covers all of those x values between those two. So from 0 to 5.1. And you can see this is called interval notation with the brackets where it includes it, or you can see it as between 0 and 5.1 are all of the x values. Notice how it's always between. So we're going to focus on writing our domain both ways. So you can see it here or in interval notation. So now we're getting into these problems where you need to see the visual of the graph, right? So this is now going into Desmos graphing calculator and graphing these so that now you can get a visual of the graph. So we're talking about here in this problem, a hot air balloon. And this is what is represented by the hot air balloon. So go ahead and make sure to pause the video so that you can graph this in Desmos. And so your graph could look a little something like this. So like you can zoom in, you can zoom in, you can zoom out so that you can see it. But notice how it's a very tall, very skinny, right? Now, notice how there's your maximum. See, at 144. So there's our maximum, there's our vertex. I could also see my y-intercept. Now it's a little hard to tell because of how skinny, but I mean, we could zoom in and notice how you can click, right, on the graph to see where it is, which is here at 0, 80. So this is our graph here that we're working with to solve this problem. So what I did and now notice here, here's our x-intercepts. What I did I went ahead and I made this graph here so that now it's a little bit easier for us to see. So looking at the first question is just asking us, what is the y-intercept and what does it mean? So here we go. Well, what is the y-intercept? 0, 80, right here. So like what we showed when we were looking at Desmos. So the hot air balloon has this y-intercept of 0, 80. Which means what? Well, it means that the hot air balloon started at what height? 80 feet. So it started at 80 feet. And again, we know it's feet because our height is in feet here. Now, notice here, this is what we were talking about with the reasonable and keeping in mind the situation. There is a positive and negative x-intercept for this function. What is the positive x-intercept? And we're going to explain what this means. So here, looking at the positive x-intercept is 5, 0. Notice how the x-intercept over here is negative 1, 0. So we're going to focus on the positive. So our x-intercept here is 5, 0. So now let's think about this. Why do you think I'm only asking for the positive x-intercept? Remember, this is not just any graph. This represents the hot air balloon in the air. So if you were to think about this in context of the situation, could the graph or time, the hot air balloon, travel in a negative time here? No. So truly, does it make sense that we're going to include this section of our graph? Well, no, because again, you can't consider something using negative time because this is all in the negative. So really, to make this reasonable, we're just going to focus on the positive x values because that is going to be your time. So that's why we're only focusing on the positive 50. And again, what does that mean? That means that the hot air balloon, right, started at 80 feet above the ground and traveled for how long in the air? 5 seconds. Now identify what time the hot air balloon will reach its maximum height. So here we go, maximum height. So what are we looking for? The vertex. So looking at the vertex, what is the maximum height? Right here, 144 feet. So the vertex is at 144. So what time, though, did the hot air balloon reach? So it reached 144 feet in 2 seconds. So it took 2 seconds to reach the maximum height. So now what is the reasonable domain? Going back now to the purpose of identifying reasonable, right? Because, sorry, wrong direction. Reasonable. Remember, we're talking about all x values. So technically, this graph covers all x values from -1 to 5. But again, does it make sense to include these negative values? Can you travel in negative time? No. So we're going to only focus on here. This is what makes this situation a reasonable domain. We're starting at 0 and we're ending at the x value of 5. So that is what we now mean by making sure that the domain is reasonable, the x value. So from 0 to 5 or 0 to 5, our x value is covering all between. So same thing, let's go ahead and let's do our next problem. Go ahead and graphing. So we're talking about the path of a golf ball and graphing that in Desmos. So if you need to, go ahead and pause the video so you can graph it. And so when you graph it, it looks something like this. And again, you can zoom in, zoom out. So notice, and we can identify all of our pieces. And if you click on the graph, you can see all 4 of those points. Here's our y-intercept. Here's our maximum. And here's our x-intercepts. So notice that you can identify those points, these attributes here in Desmos. I'm going to go ahead and I've already also saved it here as well. So it's that same image. Approximately how long is the golf ball in the air? Now again, what part of the graph do you think now, because this is just a graph, right? But keep in mind, we're actually talking about the path of a golf ball. So what section of the graph are we not going to use? This negative, right? Because can you have a golf ball traveling in negative time? No. So we are only going to use this section of the graph. That's it. Because the golf ball is starting here at 0, and then its height, and then continuing on its path. So again, approximately how long is the golf ball in the air? Well, the golf ball is in the air starting here and ending at 5 seconds. Because remember, right, the x-axis represents the ground. So here, oops, sorry about that. So the golf ball is in the air for 5 seconds. How long does it take for the golf ball to reach its maximum height? So how long? How many seconds? So you can also go back to your graph here and notice how long did it take to reach that maximum height? 1.75 seconds it took to reach that maximum height of a little over 21 feet. So 1.75 seconds. And what is the y-intercept for this function? 0.15. So notice you should have seen that 0.15 here. So the y-intercept is 0.15. Now, what does that mean in context of the situation? That the golf ball started and they recorded it starting at 15 feet in the air. So go ahead now and pause the video and graph this and answer these 3 questions on your own, and let's see how you do. And here we go. So first off, when you graphed this, talking about the path of a soccer ball, your graph should look something like this, right? And then you can identify all of those parts too. So like you can identify the y-intercept, which is at 0, 18, the vertex, the maximum, and your 2 x-intercepts here. However, we're talking again about the golf ball traveling in time and recording its height in feet. What part are you not talking about? All of this negative, right? So keeping in mind, you needed to make sure to not look at those pieces and answering the questions here. So for the first question, what is the maximum height? So what is the maximum height reached by the soccer ball? So you should have used the vertex. So what is the maximum height? A little over 28 feet. It took a little over 2 seconds for it to reach 28.125 feet. So 28.125 feet. What is the positive x-intercept, right? Because we don't need that negative because you can't travel in negative time. So you should have said that this is 6, 0. And what does it mean? Well, it means that the ball, the soccer ball, was in the air for 6 seconds before it hit the ground. Now, what is the reasonable domain? Because again, right, domain is all x values, which technically all of the x values are the going on and on and on, or we can say -1.5 to 6, right? Or going negative to positive, however, reasonable. So again, right, because you can't travel negative time, we are starting x values for reasonable are starting at 0 and ending at what x value? 6. So here, your domain is at, oops, sorry, not that, right? So from 0 to 6, or x values are all between 0 to 6.